Hello, everybody. Let's take a look at AP Chemistry, Chapter 3, Section 2, taking a look at empirical and molecular formulas. What we're doing with this concept is, for example, we have a compound that we run through something, a mass spectrometer. Sometimes they give us percentages. We don't know what this compound is in its actual composition in terms of ratios of carbons and hydrogens, oxygens, that kind of thing, but it will give us information like it's in a certain percent. Okay, so what we do with those numbers is we develop what's called an empirical formula first, and then from there we develop a molecular formula. So let me talk about the differences between those first. An empirical formula is what the compound would be in identity in its simplest form, and that's key. That's going to be our first step of things. And by simplest form, I mean this. If I have a ratio, a compound, for example, of carbon and oxygen, I might find in its simplest form that compound has one carbon for every two oxygens. That would be the empirical formula. I might have, for example, within the compound that I have one nitrogen for every three hydrogens. That's in its simplest form. Or I might find that I have, in a more complex compound, I have one carbon, I have two hydrogens, and one oxygen. Okay, that's its simplest form. When I get into the molecular form, that's its true form. That's its more complex form. That's its true identity. Okay, so the first thing we need to do is figure out what a compound is in its simplest form, and then we find its true identity from there. So pay attention to those terms, empirical versus molecular formula. Now, the reality is sometimes what we find for its simplest form is also its true form. So if I've figured out things to be in its simplest form CO2, and it indeed did become carbon dioxide or was carbon dioxide, that's also considered a molecular formula. Same thing for ammonia. I figure out in its simplest form it was a ratio of 1 to 3 for nitrogens to hydrogens. But when I do more math with it, I realize, nope, that's actually the ratio it's in. Then I would say that it's empirical as well as molecular. But not everything is going to be in its simplest and true form. What we're looking at here in its simplest form of CH2O might be something like C6H12O6, commonly known as glucose. So you see the empirical formula here is just simply a reduced version of the molecular formula. Okay, so that's how all this works. Now let's take a look at how we approach those things. These numbers right here are actually mole ratios of the different atoms we find within a compound. Okay, so let's take a look at the first set of examples here of taking a look at a compound that contains carbons and hydrogens and nitrogens. We've got a compound in there. I want to know, after with this data we've got in there, whatever this compound is, 38.6 grams was carbon, 16.22 is hydrogen, 45.11 was nitrogen. I want to know what it is in its simplest form. Well, let's convert everything to moles. So to do that, I have 12 grams for every mole of carbon. I have 1 gram of hydrogen for every mole of hydrogen. And lastly, I have 14 grams of nitrogen for every 1 mole of nitrogen. Okay? And so what I've done at this point is I've figured out, or I'm converting everything into moles. So this ends up being 3.22 moles of carbon, and this is 16.22 moles of hydrogen, and this ends up being 3.22 moles of nitrogen. Now, within that compound, for every 3.22 I've got of this, I have 16.22 of this and 3.22 of this. That's really clunky numbers to deal with, so we divide everything by the smallest number of moles. That's step 2. Divide everything by the smallest number of moles. That gives me a 1 to 5 to 1 ratio. Much easier to be working with. And so I can deduce from this that my compound that contained carbon and hydrogen and nitrogen in its simplest form was CH5N. Okay, that's the empirical formula for the compound. I don't know what the true form of the compound is because I don't have any more information to work with. Now let's take a look at another example where I'm given a little bit more information. This is giving me some information about the molecule of caffeine. I ran it through the mass spectrometer, and it gave me that I have 49.848% of carbon within that compound and so on, but it doesn't tell me how big the compound was. So I don't really know what to do with it, whereas here they gave me the grams already, and so I could just convert grams to moles, I'm done. But here they didn't tell me how much. And it truly doesn't matter because if I have a little or a lot, I'm still getting the same percentages. So let's do ourselves a favor. Let's assume we have 100 grams. That's going to make our life easier because if I have 100 grams of the sample, then I have 49.48 grams of carbon. I have 5.15 grams of hydrogen. I have 28.87 grams of nitrogen. And I have 16.40 grams of oxygen. Now it's the same game. Convert everything to moles. And so this is 12 grams per mole. This is 1 gram per mole. This is 14 grams per mole. And this is 16 grams per mole. Okay, those are all grams to moles. And so what I end up in terms of numbers here is, let's see, I end up with 4.12 moles of carbon. This ends up being 5.15 grams of moles of hydrogen. This ends up being 2.06 moles of nitrogen. And lastly, I end up with 1.025 moles of oxygen. Okay, now remember the next step. Step 2 is always divide everything by the smallest number of moles to get our simplified ratio. So I'm going to divide everything by 1.025. And lastly, 1.025 here. This tells me that in its simplest form, the compound of caffeine is going to be 4 carbons for every 5 hydrogens, for every 2 nitrogens, for every 1 oxygen. So if I was going to write that out, I have C4H5N2O. That's in its simplest form. Now, I want to know its true identity, and to do that, I want to know its molecular formula. To do that, I defer to my molar mass. What it says is the molar mass is the mass of 1 mole of the entire compound in its real form. That mass is 194.2. So the question is, how much bigger is this compound than the empirical formula? Remember, this is my empirical. So the question is, what's the mass of this? So I go 4 carbons. If I had a mole's worth, I have 4 carbons. I have 5 hydrogens, I have 2 nitrogens, I have 1 oxygen. This is 12, this is 1, 14, and 16. So 16, 28, 5, and 48. That formula mass of the empirical formula ends up being 97 grams per mole. So the mass of the empirical formula is 97 grams per mole, but the molecular formula is 194. How much bigger is that molecular formula? Well, if I divide my 194.2, if I divide my molecular formula by my empirical formula mass, I end up with the molecular formula being 2 times greater. Okay? So I just took the formula mass of my empirical, divided it from the empirical mass, or the molecular mass, and I found that the molecular formula was double that of your empirical formula. So that means I multiply everything inside. So I have 2 times the carbons. I have 2 times the hydrogens. I have 2 times the nitrogens. And I have 2 times the oxygens. There is the equation for the molecular formula for your caffeine. Okay? So that's that step. Now we're taking a look at applying this concept of formula masses and everything else to find other items. Okay, so this is sample problem number 1 that we've got in our notes, taking a look at some of the problems. Now, we are given an equation where we have this unknown compound. Okay, we know the compound contains carbons and hydrogens, but we just don't know how many. We do know that we've got carbon dioxide and we've got water because we masked those out. And notice that within carbon dioxide, the carbon component is here and the hydrogen component is here. These both contain oxygen, but they're here. And the law of conservation of mass states that whatever we've got in product side must equal the mass on the reactant side. I just want a piece of the carbon dioxide. I want a piece of the hydrogen to find the components of my unknown compound. So what I want to do is the same concept. I want to figure out within carbon dioxide, I want to focus on just the carbon aspect. So I'm going to take 2.641 grams of carbon dioxide, and I'm going to convert that to moles of carbon dioxide. Okay, 1 mole of carbon dioxide ended up being, what is that, 44? Yeah, 44 grams of carbon dioxide. Now, within carbon dioxide, this is the tricky part. I'm not focused on the carbon dioxide, but just the carbon in there. So I ask the question, if I have 1 mole of carbon dioxide, how many moles of carbon atoms would I have in there? Well, notice it's a 1-to-2 ratio. So if I have a mole's worth of carbon dioxide, that means within that compound, I have 1 mole of carbon atoms. And so if I look at that, I have, within that sample, I have 0.06 moles of carbon atoms. Now doing the same thing with water, 1.442 grams of water. Let's convert that into moles. 18 grams of water to moles of water. And I ask the same question. If I had a mole's worth of water, how many moles of hydrogen atoms would there be? And notice it's a 2-to-1 ratio. So I have within water 2 moles of hydrogen atoms. And so what we end up with in calculating out your water is 0.16 moles of hydrogen atoms. What does that tell me about my compound? Well, however many atoms I had in here, they've got to be in here because there's no other place for the hydrogens to come from. Whatever I had in carbon dioxide for carbon must have come from there. And I already found that I had this many moles worth. So I do the same game I did on the previous slide with empirical formulas. I divide everything by the smallest number of moles. And so I find within my compound, I have a 1 to, in this case, this ended up being a 2.7. That says I have, for every 1 carbon atom, I have 2.7 hydrogen atoms. And obviously you can't do that. You can't have 2.7 atoms of something. It doesn't split. If I doubled this, that wouldn't help anything. But I'm going to end up actually tripling this. If I triple this, I get nice clean numbers to work with. This means that I have 3 carbons for every 8 hydrogens. My empirical formula, or sorry, my chemical formula for this compound ends up being C3H8. Okay, so that's how we find the identity of an unknown compound when we know both of our products. But that's not the real scenario all the time. If I know both the products, that's one thing. But what happens if I don't know both the products, but I do know I know how much compound I started with? This is actually a more real example than people realize. You can measure how much you started with, and you can measure how much water was given off. That's a more real example. And so let's take a look at how to solve a problem like this. We have our equation already there for us. And so we take a look and we see the same components. Within my water, I can see how much hydrogen. Okay. The problem is the oxygen, and I don't have a way of figuring out my carbon. So I have to do something else. Law of conservation of mass says whatever I have on one side must equal the other. If I can figure out how many grams of water are over here, and how many grams of, not of water, of hydrogen are over here, I can figure out how many grams of hydrogen are in my compound, and then I can subtract my grams of hydrogen from the overall compound. That's the big picture. So let's see what that looks like. All right, so let's take a look at my water first, and I have, notice it's in milligrams. To do the mole conversion, we have to be in grams. So I'm going to start with 0.0428 grams of water. Okay, got to convert to grams first. We know that there's 18 grams of water in 1 mole of water. And remember the trick of this, within 1 mole of water, I have 2 moles of hydrogen atoms. Okay. I have 2 moles of hydrogen atoms. But since I need to figure out the mass of my hydrogen here, because I don't know the carbon at all, I want to figure out how many grams of hydrogen atoms there are. So 1 mole is going to be 1.01. We'll just call it 1 gram. I could have done particles, I could have done all those things, but it's 1 mole's worth is grams. And so what I end up with, in terms of just the math, I end up with roughly 0.00476 grams of hydrogen. That means that within this compound, whatever this ratio is, I started with 0.0476 grams was the compound. Of that compound, 0.00476 grams was hydrogen. So what that tells me is within the compound, I end up with 0.0428 grams of carbon present. So now I have all my pieces. Within this compound, I have 0.00476 grams. Within this compound, I have 0.0428 grams of carbon. So let's take that 0.00476 grams of hydrogen. Let's convert that to moles. And what I'm trying to do now is find my ratio. Remember, those are always mole ratios. So let's take 0.0428 grams of carbon, and let's divide that by 12 grams of carbon to moles of carbon. And so this will end up giving me, let's just check my numbers. This gives me 0.00476 moles of hydrogen for every 0.00357 moles of carbon. Well, what does that mean? That means it's a ratio of those things. We divide by the smallest number of moles. That says for every, I got 1 carbon, and that ends up giving me a 1.3. For every 1 carbon, I get 1.3 hydrogens. Again, you can't split the atom, so let's multiply everything by 3, and that will give me a 3:4 ratio. What's my compound? My compound is C3H4. Okay, so that's how we do problems of that nature to try to figure out how do we go and get from data we collect, how do we go and figure out the true identity of a compound when we know the reaction and so on. This is going to lead us into problems 1 through 4, and notice that we have a pre-lab that does the same thing with copper and building up to the copper and iodine. And this scenario is the same thing where we're going to be reacting silver and chlorine gas in the pre-lab, and the lab itself is going to be copper and iodine. There's some practice problems with that. You should have everything you need to do practice problems number 2, assignment number 2, the pre-lab, and that will get you primed up for the copper and iodine lab. All right, good luck.